Hello, my name is Davis Binger, and let's talk about vector projection. Today we will be looking at problem 2 of the 12.3 handout. We consider two vectors, u and v. U is equal to 5, 0, 15, and v is equal to 4, 1, negative 1. We are then asked to calculate the projection of u onto v and the scalar component of u in the direction of v. Recall the formulas for the projection of u onto v, which is u dot u divided by v dot v multiplied by the vector v. And the scalar component of u in the direction of v is u dot v divided by the magnitude of v. Now, it's an easy matter to calculate these quantities and to apply the basic properties of vector analysis to multiply a scalar times a vector. But let's spend a moment to discuss what the projection of u onto v is and what the scalar component of u onto v is. Take a closer look at u. Embedded in our notation for u is projection values. We look at u, and u is what? It's 5 in the x direction, 0 in the y direction, and 15 in the z direction. U is 5 times the vector 1, 0, 0 plus 0 times the vector 0, 1, 0 plus 15 times the vector 0, 0, 1. So the projection of u in the x-coordinate is 5, the projection of u in the y-coordinate is 0, and the projection of u in the z-coordinate is 15. Projection and the scalar component of u in the direction of v allow us to take vectors and consider them under new coordinate systems. This is incredibly useful in various physical applications, in physics and engineering. I'll give you one example of that. If we have a block on an inclined plane sitting here, we may be interested in how the force of gravity affects the block's movement on this inclined plane. So the vector for gravity will be pointing straight down, but we really want to calculate the component of this force, this gravitational force, in the direction of the plane. It's not suitable to consider our traditional x and y axes in this case. We need to consider the axes, which is the plane. So we need a new coordinate system. The projection of u onto v and the scalar component of u in the direction of v allow us to consider non-standard coordinate systems. And that can be really useful for all sorts of physical applications. But let's just now return to the mechanics of calculating these. Well, one is a vector and the other is a quantity. So what do we need? We need u dot v, we need v dot v, and we need the magnitude of v. What is the dot product? The dot product is the sum of the pairwise multiplication of each coordinate. So we take the product of the x-coordinates, add them to the product of the y-coordinates, and add in the product of the z-coordinates. In this case, the product of the x-coordinates is 5 times 4. 5 times 4. The product of the y-coordinates is 0 and 1, and the product of the z-coordinates is 15 times negative 1. When you simplify this, you get negative 5. For v dot v, you just sum the squares of each component, or 4 squared plus 1 squared plus negative 1 squared, which is 16 plus 1, or 18. And the magnitude of v will simply be the square root of v dot v, or in this case the square root of 18, and which is simplified to 3 square root of 2. Now, plugging into our formula for the projection of u onto v, this gets us u dot v, which is 5, divided by v dot v, which is 18. So that's 5/18 times v, which is 4, 1, negative 1. After distributing the 5/18 into the vector v, we arrive at our final answer, which will be the vector 10/9, 5/18, negative 5/18. Alright, finally, the scalar component of u in the direction of v will be given by u dot v divided by the magnitude of v, which will be 5 divided by 3 square root of 3, and after moving the square root of 2 into the numerator, we get 5 square root of 2 over 6. Okay, this concludes our problem. Thank you for watching. And as always, you can contact me by leaving a comment below or writing an email to me at binger@math.ohio-state.edu. Thank you, and have a good evening.